Greetings. I am Ankit Shukla, a research scholar at Bennett University from India. In this presentation, I'll unveil our work titled Opinion Unaware Image Quality Assessment via Adversarial Convolutional Variational Autoencoder. We'll explore the challenges and breakthroughs in the blind image quality assessment methods, focusing on synthetic distortion and their real-world relevance. As we move forward, we'll begin with an introduction to the field of blind image quality assessment. We'll then go through the related work, highlighting the significant contribution. Identifying research gap will be crucial as it reveals the motivation of our study. Our proposed methodology introduces a novel approach to tackle these gaps. We'll present our result demonstrating the effectiveness of our method. Finally, a key point summary will encapsulate the essence of our findings. The journey of an image from acquisition to storage is susceptible to potential degradation. Compression affects the quality of an image. Also, the transmission of a digital image can result in loss of data, especially in low bandwidth conditions. Finally, storage can also contribute to the degradation in digital images. During the subsequent image processing, these degradation directly affect the performance. For example, the reliability of disease diagnosis depends upon the clarity and accuracy of the images. Any degradation can lead to misinterpretation with dire consequence of the patient care. This is where image quality assessment comes into play. Image quality assessment is not just about algorithm metric, it's about ensuring that the images we rely for critical decisions that are as close to the original quality as possible. Image quality assessment methods can be categorized into three categories based on the availability of reference image with the corresponding distorted image. Full reference method require a pristine reference image to compare against the distorted image. They have shown excellent performance when the complete reference image is available. Reduced reference method on the other hand work with only partial information from the reference image and still manages to deliver promising results. However, in many real-world situations such as with authentically distorted image, we don't have the luxury of reference image. This is where no reference methods comes in handy. They assess the perceptual quality of images without needing a reference. No reference method can be further classified into supervised, weakly supervised, and unsupervised blind image quality assessment methods. Supervised methods employ a supervised regression model trained on distorted images alongside their corresponding mean opinion score. Mean opinion score is a subjective score reflecting the perceived quality of an image. These methods are often referred to as opinion-aware blind image quality assessment methods. Weakly supervised methods are often depend upon full reference methods to derive what is known as pseudo-subjective score. However, this reliance on reference image or subjective score can be a limitation, especially in real-world scenarios where such references are unavailable. To address this, some researchers have explored no reference methods that do not depend on the image quality score. It is important to note that most opinion-aware blind image quality assessment methods have been developed for a specific type of distortions. Often those are synthetic. These methods have been fine-tuned to address a particular degradation pattern that are predefined and controlled. However, the real world presents a far more complex picture. Images can suffer from many authentic distortions, those that occur naturally and unpredictably. These can range from sensor noise in low light condition to compression artifact during transmission. We introduce a novel framework that utilizes a reconstruction-based strategy. Our approach is centered around learning quality-aware features directly from the pristine images, those without any distortion, and then use the learned distribution to evaluate the image quality. Our proposed framework is composed of two integral modules. Module 1 is the pristine data distribution learning. Here, we focus on capturing the distribution of undistorted images. By employing the reconstruction techniques, we can learn a comprehensive distribution that represents the gold standard of image quality. The second module or the second stage is the utilization of learned distribution for unsupervised image quality assessment. With the pristine data distribution as our benchmark, we can now assess the quality of new images in an unsupervised manner. This means that our system does not rely on any external references or human-generated score. Instead, it compares the features of the test image against the learned distribution to evaluate its quality. We will be discussing these modules in detail further. In first stage, we train a CVI GAN to learn to generate pristine images. Training of CVI GAN use the combination of adversarial learning along with an unsupervised approach. The convolutional variational autoencoder consists of an encoder and a decoder. The encoder generates a low-dimensional representation of pristine images. We can name this low-dimensional representation as latent code or latent representation. Then, a decoder uses this latent code to generate the pristine images back. To enforce the latent distribution must belong to a pristine image distribution, we use scale divergence laws. And to ensure the enhanced perceptual quality of a reconstructed image, we also use VGG laws, and a discriminator is employed to take the advantage of adversarial learning. In the second stage, we use the learned weights of an encoder for inference. We pass the set of pristine images, noisy images, and degraded images to the trained encoder and plot the latent representation of all the images. As we can see in the plot, pristine images denoted from red color lies closer, whereas the latent representation of noisy and degraded images represented with the green and blue color are very far from the pristine image's latent representation. This shows the clear separability and the deviation. We use this deviation as a pseudo indicator of image degradation. To quantify this deviation, we employed a latent distance metric which can be denoted mathematically as shown. We evaluate the performance of our proposed net framework on 5 benchmark datasets. Also, among the selected blind image quality assessment methods to compare, NIQE, LINIQE, and MA19 are these unsupervised methods. Rest are the opinion-aware methods. As we can see from the table, supervised or opinion-aware methods that are trained on large datasets or a combination of datasets do not show the generalized performance on the dataset having synthetic and authentic distortions. As our proposed method, which is using an efficient training strategy, outperforms almost all the unsupervised methods on both authentic and synthetic distortion datasets. Besides that, our proposed framework delivers the comparable performance against the other supervised methods that are either rely on opinion score at some stage or are trained on both distorted and its corresponding pristine images. This highlights the effectiveness of our proposed training strategy to learn the quality-aware features and its generalization applicability. We also conducted the performance evaluation of our proposed framework for the different distortion and compared it with some opinion-unaware methods. As it is clearly visible from the table, our proposed framework can handle diverse and complex distortion. From these graphs between our proposed latent distance metric and the mean opinion score of two different datasets, it is clearly visible that our proposed latent distance metric is highly correlated with the subjective quality score. Apart from the performance comparison with other image quality assessment methods, we also conducted few ablation studies as well. In one ablation study, we compare the performance of different loss functions used during the training stage. In this study, we first used mean square error loss in combination with scale divergence loss. Then we used VGG loss in place of mean squared error loss in combination of KLD loss. Later, we added discriminator loss in this combination as well, as it is evident from the table that our proposed combination provides the best results. In another ablation study, we compare the different quality metrics with our proposed latent distance metric. This study justifies the selection of our proposed latent distance metric over the other metrics. This is the visual results for ablation study for different loss functions at training stage. As it can be seen that our proposed combination of loss function provides the best PSNR amongst the other combination. Finally, to conclude, here are some of the key takeaways from this presentation. We presented a novel training strategy using the adversarial convolutional variational autoencoder for opinion-unaware blind image quality assessment. We designed a combination of loss function which allows the content-agnostic and quality-aware feature learning. Result analysis shows the performance superiority on variety of benchmark datasets that contains authentic as well as synthetic distorted images. Our proposed framework permits the opinion-unaware image quality assessment in real-world scenarios. These are the references that Thank you and have a wonderful day.